we need to prove that this is true for all n. So probably for all natural n, starting from 1, 2, 3, 4 integer numbers for n 1, 2, 3, and so on. For the sake of analysis, we can try to write out first couple values of n. So if n is 1, just so the trying to understand what's n plus 1, 2, 3, n plus 1 means. So for n plus 1, this is going to be 1 over, so 1 plus 1, so it starts from the number right after the 1 and goes until to number that's 3n, 3 times 1 plus 1, so up to 4. And this is less than 2. For n is equal to 2, you start with the number right after the 2, so it starts with 3 and goes up to 3 times 2 plus 1, that's 7. So 1 over 7 less than 2. So the difference between first and 2, so this one has this extra term here and this one has these 3 terms. So 3 and 4, 3 and 4, these are like common terms in both of them. How about n is equal to, okay, how about n is equal to 3? We start with 4 and go up to 1 over 6. So 3 times 3 plus 1, it goes up to 10, right? 1 over 7, 1 over 8, 1 over 9, and 1 over 10. So if you compare the second one and the third one, the common terms are these, the 4 terms. These 4 are the common terms. And then there are 3 extra terms here and 1 extra term. So if you want to do induction, when you go from n to n, from k to k plus 1, you can see that there will be 1 extra term in the k and 3 extra terms in k plus 1. So that's the difference between k and k plus 1, the sum value of n and the next one. So here again, so the first term and here 3 extra terms. So if I do the common denominator for base case of induction, 2, 3, 4, that's common denominator is 12. And then if I, the denominator is 6 plus 4 plus 3, so it's 13 over 12, so it's between 1 and 2. So the base case of induction is true, but the main observation is that when you transition from a number to the next number is like plus 1, this one, and then these 3. So basically we have the base of the induction. It's true for n is equal to 1. You can actually evaluate n is equal to 2, n is equal to 3, and then prove it. So we have the base. So the step of induction, assume that n is equal to k is correct, and we want to prove n is equal to k plus 1. So if I say sk, the sum of sum k, 1k plus 1, 1 over k plus 2, 3k plus 1, and what I'm assuming in the step of induction is this sk is between 1 and 2. So what will be sk plus 1? Sk plus 1 is going to be, it will start from k plus 2 all the way to 3k plus 1 plus 1, right? This is 3k plus 4 if you open the parentheses. And we want to prove that this is sk plus 1 is also between 1 and 2. So what's the relation between sk and sk plus 1? So if I try to write the sk plus 1 in terms of sk, so let's say we have sk, and then sk has this one extra term, so I have to remove that extra term, subtract it. And as you remember from before, sk plus 1 should have 3 last extra terms, so 3 that would be like 3k plus 4, the last one, 1 over 3k plus 3, and 3k plus 2. So this is the relation between sk plus 1 and sk. So what I want to do is probably simplify this expression, simplify this part of the expression. Okay, if you simplify this part, you get sk plus 1 is sk plus something, very small step. So this is a small positive number greater than 0. So what you get, which this means that sk plus 1 is greater than sk. So this is good to prove first part of the inequality, right? So we have that s1 is greater than 1, and then using this you can see that s2 is greater than that, and then s3 is greater, and s4 is greater, and so on. All of these numbers are greater than 1. So we have done with this, we are done with the first part of the inequality. And for the second part of the inequality, here there is no need to use the induction. We will just increase the number. So say 1 plus over this one is equal. How about if I compare 1 over n plus 2 with 1 over n plus 1? Since the denominator is less, so this one is going to be greater, right? And so on. If I do for all of these numbers, this is going to be 1 over n plus 1, less than. All of these numbers are less than 1 over n plus 1. So this sum Sn will be less than, so each of the numbers is less than 1 over n plus 1. So we have here 2n numbers. So it means 2n multiplied by 1 over n plus 1. If I do the product, it will be less than this, which is 2n over n plus 1, which is less than 2. So by just increasing the numbers, each of the number by 2n plus 1, we can still get a number that's less than 2. So this sum Sn is way small than 2 compared to 1. So the first part of the problem is induction. We prove by induction that the sum is greater than 1, and the second part is just taking this sum. So we can just do this summation. On the left of this summation you get Sn, and since you sum all of them, you get less than, and then 2n 1 over n plus 1, and it's less than 2. So this is how you prove the inequality.